Dear student, warm welcome to NPTEL Phase 2 program video course on geosynthetics engineering in theory and practice. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. The name of the course, Geosynthetics Engineering in Theory and Practice. This is module number 13 and lecture 61, Designing with Geofoam. I will now focus the recap of the previous lecture, that is application of geofoam as thermal insulation, installation of geofoam, design of a magnet using geofoam, that is check for bearing capacity, hydrostatic uplift, hydrostatic horizontal sliding. Now, I will address or continue this example, that is D, overturning due to the seismic effect. The factor of safety against overturning due to seismic effect can be determined from the following equation, that is factor of safety is equal to summation of the stabilizing moment by summation of overturning moment. Now, summation of stabilizing moment is equal to 0.5 into RW into W of GF plus WP and T. You know that RW is the base width of the pavement and WGF is the weight of the geofoam material and WPT is the weight of the normal pressure and the traffic load which is given. And overturning moment is equal to 0.5 into H. H is the height of the embankment, KH into W into G of F. KH is the seismic coefficient in the horizontal direction, plus TGF plus 0.5 into TP into KH into W into P and T, where TP is the thickness of the pavement and TGF is the thickness of the geofoam. So, factor of safety can be written is equal to 0.5 into RW into WGF plus WP and T divided by 0.5 into H into KH into W of GF plus TGF plus 0.5 TP into K of H into W, P and T. So, now we know that RW is equal to the 12 meter, it is given. So, 0.5 into 12 into W of GF weight we have calculated, that is 38.88 plus W of PT, that is weight of the normal pressure and the traffic load, that also is given 21. This divided by 0.5 into the height of the embankment 6 meter into this seismic KH value horizontal is taking 0.2 into weight of the geofoam which we have calculated earlier, that is 38.88 plus this is the thickness of the geofoam, that is 5.39 plus 0.5 into this is thickness of the pavement or cover, that is 0.61 into KH again is equal to 0.2 into WPT is given 21. So, you can have 359.28 divided by 47.247 So, this will be equal to 7.6. So, factor of safety due to the seismic effect for overturning it is 7.6. Now, here is the relationship between the thickness of the geofoam and the factor of safety against this overturning. So, this is for a particular road width is about 12 meter and the gamma of EPS is equal to 18 kg per meter cube, and this horizontal axis is the height of the embankment and vertical axis is the factor of safety against this overturning. So, here you can see that factor of safety due to overturning is reducing with the increasing the height of the embankment. Now, from this design chart, let us say for a height of embankment about 6 meter and thickness of the geofoam mean H minus cover soil, that is 6 minus this cover soil will give 5.39 meter, and top width of the geofoam is 12 meter, because that is the road width 12 meter. Then you can calculate that factor of safety from this chart. Let us say that the height of the embankment is 6 meters somewhere here, and then you move up, and then suppose it will meet somewhere here, and then you move on the left side and it will meet somewhere in between 5 and 6. So, this will be about 5.5. So, factor of safety can be approximated by taken as 5.5. Now, the location of the resultant force from the top of embankment can be determined as follow, that if the location is distance is x, x is equal to summation of stabilizing moment minus summation of overturning moment divided by summation of normal stresses. Now, what is the summation of normal stresses? That is equal to the summation of n, and that is due to the W of GF plus W of P and T. We have calculated earlier W of GF 38.88 and W of PT is given 21. So, this will give that summation of normal stress is equal to 59.88 kilopascal. Now, you can calculate the x using this equation. So, x is equal to stabilizing moment, already we have calculated 359.28, overturning moment also calculated 47.247, and here the normal stress which we calculate now 59.88. So, you can obtain the value of x is equal to 5.21 meter. Now, E is the eccentricity is equal to, this is 12 by 2 minus of x, that means 5.21. So, this will give that eccentricity E is 0.79, and this is RW is the road width, that is 12 meter. So, 12 divided by 6 is equal to 2. So, this is less than 0.79. Since E value is less than RW by 6, that is 2. So, no tension criteria for the embankment is satisfied. Now, what is the maximum soil pressure Q max under the embankment can be determined as follow, that is Q of max is equal to summation of n divided by RW into 1 plus 6E divided by RW, which should be less than the Q of A. So, we will calculate also Q of A, what QA is allowable soil pressure. Now, Q maximum is equal to summation of n, we calculated 59.88 divided by RW road width is 12 meter, then 12 into 1 plus 6E, we calculated 0.79, this is E value is 0.79. So, you put 0.79, this divided by RW again is equal to 12. So, this will give you that what is the maximum soil pressure Q maximum is equal to 6.96 kilopascal. Again, we know that allowable soil pressure, that is Q of A, is equal to Cu into 5 divided by 3. So, Cu value which is given 15 into 5 divided by 3, that equal to 25 kilopascal, which is greater than the Q of maximum. So, you have calculated Q of maximum. So, this value is greater than the Q of maximum. Therefore, Q maximum less than the Q of A, that means allowable soil pressure, that means it is okay. Now, E, translation due to the wind, because geofoam is material is very superlight material. So, you have also take into consideration if there is a wind and how you can design for the wind analysis, how can you do that, because this is very important, because when you will construct the embankment on the subgrade soil using the geofoam material, and because for its lightweight material there is a possibility for the fly of the geofoam on that locality. Therefore, it is require that wind analysis. So, we will consider that what will be the wind velocity in that locality and how you can calculate this design for the wind velocity. So, here this is the wind direction we have considered, and the velocity of wind about 40 meter per second, and this is wind analysis after Stark ETL 2004, and this is the P of U, that means this is the pressure distribution in the upwind direction, pressure distribution in the upwind direction, this is P of U, and here is the P of D, that means this is pressure distribution in the downward wind direction, okay, and this slope is the 1 vertical to 4 horizontal, and this is the theta of U, this angle, that means the upwind slope angle, that theta of U, and here is the theta of D, that means this is downward slope angle theta of D, and this is the geofoam material, and it has a weight is W of geofoam, and this is the road width which is called R of W, and this is the horizontal resistance force, because wind force is acting along this direction with a velocity of 40 meter per second. So, this is R of U, I say this is the upward upwind force, this is R of U, upwind force, and this side is R of D, and which is called the downwind force, this is the downwind force. So, now we will analyze when the geofoam embankment is subjected to the heavy wind, the wind force analysis should be considered in the design. Now, the equation of the design for the wind analysis as per reference for the untitled report prepared by EDO 1994 and Miki and the Tsukamoto undated are as follow. So, this is the P of U, that means this is the pressure distribution in the upwind direction, P of U is equal to 0.75 into V square, that is this velocity of the wind into sine of theta U, and theta U you know that what is called upwind, that slope angle, and P of D is the pressure distribution in downwind direction, that is also equal to 0.75 V square into sine of theta D, and what theta D is downwind slope angle. So, now Pu is equal to Pd is equal to 0.75 into this is wind velocity 40 meter per second, that is 40 square, into sine of theta U or theta d, which angle is equal to 14.04 degree. So, this will give Pu or Pd is equal to 291.11 kilopascal. Again, that R of U, that is the upwind force. So, upwind force is equal to Pu into H, and Rd is equal to downwind force. So, Rd is equal to Pd into H. So, Ru is equal to Rd will be equal to, this is Pu or Pd, which will give you this value 291.11 kilopascal. So, here 291.11 kilopascal into H, H is equal to height of embankment is 6 meter. So, this will give you the Ru and Rd, that means upwind force and the downward force respectively is 1746 kilonewton per meter, and V here is the wind speed, and theta U theta d upwind and the downwind slope angle respectively, Ru and Rd upwind force and downwind force respectively. Now, require overturning against the sliding due to wind can be determined using this following equation, that is O required is 1.25 into Ru plus Rd divided by tan delta minus W of Gf. So, O required is equal to 1.25, and we calculated the Ru and Rd, that is 1746 from here, 1746. So, 1746 plus Rd also same, plus 1746 divided by delta value is given 32 degree, so tan 32 degree, minus this is weight of geofoam 38.88. So, this will give O required 6947.356 kilonewton per meter. Okay. Where Ru and Rd are the upwind and downward force respectively. So, here this figure shows the relationship between the required overburden pressure due to wind and height of the embankment. Here the road width is about 12 meter and wind speed is 40 meter per second, and the gamma geofoam is 18 kg per meter cube. And this is with the different delta value. Delta value is 20 degree, 32 degree and also 40 degree. And this x axis indicate the height of the embankment in meter, and this y axis what will be the required that overburden against the sliding due to the wind load. So, now from this figure you can calculate what will be the required overburden against sliding due to the wind. Now, from this design chart, let us say that height of the embankment is 6 meter and delta value is 32 degrees. So, this is here 32 degrees. So, here is the height of the embankment 6 meter, you go up and this is delta value is equal to 32, then you move the horizontal here. So, this is the required overburden against the sliding due to the wind, and this is lying between 5000 to 7500. So, it will be around 6947 kilonewton per meter. So, required overburden against sliding due to wind can be taken as 6947 kilonewton per meter from this design chart. So, you can see that we have also the calculated earlier that what will be the required overburden against sliding due to the wind about 6947.356 kilonewton per meter, and from this design chart also you can calculate that what should be the required overburden against the sliding due to wind, that is 6947 kilonewton per meter. Now, again we have to calculate that what will be the O required. So, O required should be less than gamma in P into Tp into Rw minus gamma of Gf into Tp into Rw plus W of C of S, that means weight of covered soil. Now, gamma p into Tp into Rw minus gamma Gf into Tp into Rw plus W of Cs. So, this portion gamma p, you know that what will be the unit weight of the pavement, that is 20, and thickness of the pavement 0.61, Rw that road width is about 12 meter, minus this is gamma Gf for the geofoam, that is 0.18, into Tp, that thickness of the pavement 0.61, into again Rw is equal to 12, plus we have calculated earlier what will be the weight of cover soil, that is 460.6. So, this portion will give you is about 605.68 kilonewton per meter. However, 6947.356 is greater than the 605.68. So, it is not okay. So, overburden provided by the soil cover is not sufficient. So, you have to take care for that. So, this way you have to design the embankment using the geofoam material. You have to calculate that what will be the wind forces, what will be the sliding, what will be the overturning, and you are to be provided with proper kind of the cover soil, and if cover soil does not satisfy, you have to change the design, the dimension or the thickness of the cover soil can be increased, or the slope can be the decrease, or geometrical shape of the embankment also can be redesigned if it does not satisfy all those criteria. Now, we will discuss the some of the important testing of the expanded polystyrene geofoam material. It is very interesting, and this is the first times in India we have been performed number of the various kind of the test on the expanded polystyrene geofoam material. We have taken the various density, and we will observe that what kind of density will be the suitable for the construction of the embankment, what kind of the thickness of the geofoam is required to reduce the lateral pressure of the retaining wall, and how also you are to calculate. So, for all the calculation that you are to know about that performance test, and how you are to perform the different types of the testing of the expanded polystyrene material. So, we will now discuss that some of the test as per ASTM and also some IS code specification. So, we will follow up that American Society for Testing Material specification for the conducting the different types of the geofoam with different densities. So, here I will now discuss this apparent density test ASTM D162208, water absorption test. As you know that geofoam material may absorb the water, and it has a certain limitation of the water it should absorb, otherwise you cannot use this material for the infrastructure. So, water absorption test also very important. This is as per ASTM C27201 and we approved in 2007. Compressive strain test, that is ASTM D162110. Tensile strain test ASTM D162309. Shear strength test ASTM C273C273M-07A. Flexural strain test ASTM D203-05A, and flammability test on expanded polystyrene as per IS 4671-1984. So, these are the some of the tests which we perform, and it has been performed in this institute in geosynthetic testing and research laboratory. So, we have to perform that what will be the density test of the geofoam as per STMD 162208. So, objective of this test to determine the density of the geofoam material. So, here is the test specimen. Size of the test specimen, generally it is 50 millimeter into 50 millimeter into 50 millimeter centimeter. This is as shown here, and this is the different color of the geofoam, because it will indicate what should be the density of this material. Let us say this material is A, this is the B, this is the C, and this is the D material. And each and individual material have a different density, and we want to calculate that what will be the density of this geofoam material. So, this is the EPS geofoam specimen for different density. Now, we know that density of the geofoam rho kg per meter cube is equal to mg divided by v. Mg is equal to mass of the geofoam in kg, and v is equal to volume of the geofoam in meter cube. For density of the expanded polystyrene geofoam B, let us say we are considering as a B sample, and then rho density will be equal to mg divided by v, and you can take the weight in a weight box and measure. This is 2.434 into 10 to the power minus 3. This divided by that volume of the expanded polystyrene geofoam is 1.25 into 10 to the power minus 4, that is in meter cube. So, this will give 20 kg per meter cube. That means density of the expanded polystyrene geofoam B is 20 kg per meter cube. Similarly, we have been performed for other sample number A, sample number B, sample number C, and sample number D, whose dye mass for sample number A is 1.843 into 10 to the power minus 3, volume is 1.25 into 10 to the power minus 4, that will give the density is about 15 kg per meter cube. Sample number B, that dye mass is 2.434 into 10 to the power minus 3 kg, and the volume 1.25 into 10 to the power minus 4 meter cube, and density gives 20 kg per meter cube. We have shown this calculation only for B, that is 20 kg per meter cube. Similarly, for sample number C, the dye mass is 2.745 into 10 to the power minus 3 kg, and volume is 1.25 into 10 to the power minus 4 meter cube. So, this will give density about 22 kg per meter cube. And sample number D, the dye mass is 3.703 into 10 to the power minus 3 kg, and volume 1.25 into 10 to the power minus 4 meter cube. This will give density 30 kg per meter cube. So, we have performed the all density, all kind of density, the other kind of the test for 15, 20, 22 and the 30 as per it is available in India. So, after the density test, we have also performed that water absorption test for geofoam, that is as per STMC 27201. So, objective of this test to determine the water absorption capacity of the geofoam material, and this test specimen shall be 75 millimeter into 75 millimeter, and this thickness is 12.7 millimeter. So, you can see that this is the different sample, that is for that density is 15, this is 20, this is 22 and the 30, and this is the equipment in which the water absorption test has been performed on the EPS geofoam. And this from this test I am showing you about that test procedure, 24-hour immerse method. This is completely immerse the specimen in a container of water for 24 hours. Remove the specimen, shake vigorously, whip up all surface water with a dry cloth, and immediately weight and record the mass. And then you can calculate what will be the water absorption. So, water absorption is equal to W minus D divided by D into 100. What W is equal to weight mass of the expanded polystyrene geofoam in gram, and D is the dye mass of the expanded polystyrene geofoam in gram. So, here water absorption is equal to weight mass of EPA geofoam 1.338 minus D, that means dye mass of EPA geofoam 1.322. This divided by dye mass of EPA geofoam is 1.322 into 100. So, water absorption is 3.793%. So, we can observe that this geofoam material has a water absorption capacity, and water absorption capacity is about 3.793 watt. Now, I will just now show you the table for the defined kind of the density of the geofoam material and what will be the water absorption capacity. So, here from this table you can see we have performed the density of the geofoam, that is kg per meter cube when it is a 15. The dye mass of the specimen D is 1.023 gram, and weight mass of the specimen W is equal to 1.063 gram. So, water absorption in terms of the percentage is 4.003. Now, when the density of the EPS geofoam is 20 kg per meter cube, the dye mass of the specimen D is 1.322 gram, and the weight mass of the specimen W is 1.388 gram. So, water absorption is 3.793%, which we have shown you for the density of the EPS geofoam, that in one calculation, that is only for the 20 kg per meter cube density of the geofoam. Similarly, the density of the EPS geofoam is 22 kg per meter cube. Dye mass of the specimen D is 1.490 gram, and weight mass of the specimen W is 1.537 gram. So, water absorption is 3.230%. Now, density of the EPS geofoam is 30 kg per meter cube, and dye mass of the specimen D 2.179 gram, and weight mass of the specimen W is 1.877 gram. So, water absorption is 2.721%. So, you can observe from this table that most of the various kind of the density and water absorption capacity is quite reasonable and acceptable, and this value is generally lies between 2 to 4%. So, geofoam material is also the suitable for the use of the different infrastructure project in India and abroad. So, now another very interesting test, and that is on the compressive strength of the expanded polystyrene geofoam material. That compressive property of the geofoam as per STM D1621 /10, the objective to determine the strength and the deformation property of the geofoam material in compression test. This is very important test, because for any structure there you require what will be the strength of the geofoam, what will be the deformation of the geofoam. So, you should know when you will design for any structure, use the expanded polystyrene geofoam material. This is the experimental setup in our institute, and this is the compression test setup. This is the load cell, this is the LVDT, and this is the steel plate, and this white color, this is the EPS geofoam as a specimen, and this is the electronic, that is the data logger. And from this compressive test, and this is the geofoam specimen, and you have to place the compressive test steel plate. So, this is the compressive test steel plate, which you have to place at the bottom and the top of the expanded polystyrene geofoam material for uniformly apply the load. Now, for this test, there are different size of the test specimen. So, it may be the cubical specimen. If it is a cubical specimen, that is that A is 50 millimeter into 50 millimeter into 50 millimeter. For B, it is 100 millimeter into 100 millimeter into 100 millimeter. This is a cubical specimen. And C, 150 millimeter into 150 millimeter into 150 millimeter. Also, you can perform this test as a cylindrical specimen test. So, this on the cubical specimen, this is 100, 100, 100, let us say, and this is the cylindrical specimen. So, this is 57.5 the diameter of the specimen, and this is the 50 millimeter in the height, or it may be the 115 diameter into 100 millimeter is the height of the cylinder, or it may be 170 millimeter diameter and the 150 millimeter of the height of the cylinder. So, you can see here that different types of cubical specimen and with the density. This is 15, this is the 20, this is the 22 and this is the 30, and this is all are in cubical specimen, and this right hand side here is the cylindrical specimen, and this is density is 15, this is 20 and 22 and 30 kg per meter cube. So, we have performed this compressive strain test specimen of the different density. So, from this test we can obtain that what will be the stress strain behavior of the geofoam under the compressive strength, because that you require when you apply for the construction of the retaining wall and you wanted to use the geofoam at the back of the retaining wall. So, what will be the compressive stress, what will be the deformation, and how you can calculate that what should be the thickness of the geofoam material is required at a particular density. So, here this curve is shows that this is the 100 millimeter by 100 millimeter by 100 millimeter, this is the specimen, and you have performed the number of the test. I am just showing that one of the sample which size about 100 millimeter by 100 millimeter with the different density, that is 15 kg per meter cube, 20 kg per meter cube, 22 kg per meter cube and 30 kg per meter cube. So, this is the compressive stress in kilopascal in the y axis and the x axis is the strain. You can see that nature of the stress strain behavior of the geofoam under the compressive strain. So, it is that initially it is moving little bit the horizontal, it is some strain but no stress, and then the compressive stress is increasing and then it is increasing like this. You can see in all under the all that different density, the nature of the curve is similar, and also it has been noted that there is a increasing density of the expanded polystyrene geofoam and the compressive stress also are increasing. So, when you are performed in a cubical specimen 100 and 100 millimeter per meter square per second, you can observe the nature of the curve, and it is also noted that density is increasing and compressive strength of geofoam also is increasing. But when also you can use this cylindrical specimen like this cylindrical specimen whose diameter is 115 millimeter and height is 100 millimeter. This is the test, this between the compressive stress in kilopascal and this is the strain in percentage, and the sample, as I say, that diameter is 115 millimeter and 100 millimeter in height. So, under different density you can see 15, 20, 22 and 30 kg per meter cube. Even then when you are using the cylindrical specimen, the nature of the curve is almost the same, and also there is a increasing in the density, that means increasing in the compressive stress value. So, there may be the slight difference in terms of the value of the compressive strength and the strength value. Also, it has been observed that when we are crossing at this point at a very minimum strain value, that may be the 2 to 3% strain value. After that, it is just increasing like this way. So, now you have to calculate the compressive strength from the stress strain curve. So, here is one typical stress strain curve of the geofoam. This is the cubical specimen, that is 100 millimeter into 100 millimeter into 100 millimeter with density of 20 kg per meter cube. So, you can see that nature of the curve is like this. So, this portion initially there is a required for the sitting correction. Here some percentage of the compressive strain you have to take into account as a sitting correction, and then it is this compressive stress is increasing, and with a minimum that also strain value. So, you can calculate what should be the compressive stress at the 5% strain. So, from this x axis, when the compressive strain is 5%, you move up and then you move the horizontally, and which will meet this compressive stress value is about 85.5 kilopascal. Now, you can also calculate that for the 10% that compressive strain. When it is 10%, you move up, when you meet this point here, then you move the horizontally, and you can have a compressive strain value 95 kilopascal. So, increasing the strain also increasing the compressive strain value. This is the for a particular expanded polystyrene geofoam whose density is about 20 kg per meter cube. So, this is also very important that when we will design this geofoam material for any structure, so we will consider what should be the compressive strain for a particular strain value, and particularly for the 5% and 10%. So, now calculation of the yield strain from stress strain curve. So, there is a compressive stress versus the compressive strain. This is the stress strain curve of geofoam. This is a cubical specimen of size 100 millimeter into 100 millimeter with a density of 20 kg per meter cube, and here this yield strength has been calculated, that is based on the EPS geofoam NCHRP W65 2004. So, here I say that some kind of the sitting correction, that here it is the 1%, and then you put the tangent from here, from the 1% you can put a tangent to this curve, and similarly you can put the tangent from this curve what it will meet here. So, it will give this compressive strength value is 82.9 kilopascal. So, here 82.92. So, you can calculate what will be the yield strength. So, you calculate the yield strength value, which value is 82.9 kilopascal. So, you should know that how to calculate the yield strength. This is as per NCHRP W65 2004. Now, calculate the initial tangent modulus from the stress strain curve. So, this is the stress strain curve for geofoam, that is cubical specimen of size 100 millimeter into 100 millimeter into 100 millimeter with density 20 kg per meter cube, and calculation of the initial tangent modulus EPS geofoam as based on the NCHRP W65 2004. So, here you can see, you can draw the tangent here. This you know that sitting correction is 1%, and you can draw a tangent, and you can take a slope of this curve. So, this is the y and this is the x. So, this is the elastic limit. This is the elastic limit, and at a strain is about 1.2%. So, then you can calculate that what will be the initial tangent modulus, that is E will be equal to y divided by x. So, that means slope of this curve. So, this is the initial tangent modulus which you can obtain from the stress strain curve of the geofoam, and with the elastic limit with a strain of 1.2 percentage, and this for a density of 20 kg per meter cube. So, we are now showing only here for a particular specimen and for a particular density. Similarly, we have also calculated that what should be the initial tangent modulus or what will be the compressive strength for the 5% and as well as the 10% have also been performed. Now, in this table we are showing all the test result, that compressive strength test result and the initial tangent modulus for a cubical specimen with different density. So, density of the EPS geofoam, that is kg per meter cube, that is 15 kg per meter cube, and size of the specimen 100 into 100 into 100, and compressive strength at 5% 60.87 kilopascal, and at 10% 68.67 kilopascal, and at yield 55.13%, and initial tangent modulus 2603.08. So, these are the data is very important for the design of the expanded polystyrene geofoam and as well as also for the numerical analysis or finite element analysis. So, when the density of the EPS geofoam is 20 kg per meter cube and size of the specimen is 100 millimeter into 100 millimeter into 100 millimeter, and compressive strength at 5% strain 85.54 and at 10% 95 kilopascal, and the yield strength value is 82.99, that is kilopascal. So, this portion I have shown you in calculation, and then initial tangent modulus 4277.25 kilopascal. Now, when the density of the EPS geofoam is 22 and the size of the specimen 100 millimeter into 100 millimeter into 100 millimeter, compressive strength at 5% strength is 100.65 kilopascal, at 10% strain is 112.5 kilopascal, and at yield value is 96.62 kilopascal, and initial tangent modulus is 5796.28 kilopascal. And density of the geofoam when is 30 kg per meter cube, and the size of the specimen is 100 into 100 into 100, that is millimeter cube, that is compressive strength at 5% 132.6 kilopascal, and compressive strength at 10% is 145.0 kilopascal, and yield value 124.55 kilopascal, and initial tangent modulus is 7566.91. It has been observed from this table that for the Indian condition and other, it has been observed that this material with density is about 22 and this initial tangent modulus value is about 5796 kilopascal. This will also suit for the construction of the embankment on the subsoil, or for any road construction this will be very useful. So, these data are very important when you will design the for any kind of the structure for embankment construction, or if you want to use back of the retaining wall, like that different types of the structure can be constructed using their different density of the geofoam material. And it is very important that you should know about their yield strength value and what will be the compressive strength value at the 5% and the 10% and 10%, and also you should know what should be the initial tangent modulus value, because this value also we can use for the finite element analysis, and also when you will simply design the geofoam, and these values is very important to us. Now, I will show that correlation between the initial tangent modulus and the expanded polystyrene geofoam density. So, here is the x axis is what will be the density of the EPS geofoam. We have taken the very high density from 15 to 30, and also this is the initial tangent modulus value in kilopascal, and this of the specimen is about 50, 50, 50, this is all millimeter, 100, 100 millimeter, 100 millimeter, 100 millimeter, 150 millimeter, 150 millimeter to 150 millimeter. This is all are in cubical shape. Apart from that cubical shape, we have also considered what should be the cylindrical shape, that is 57.5 millimeter in diameter and 50 millimeter in height, and another cylindrical shape is 150 millimeter in diameter and 100 millimeter in height, and another sample 170 millimeter in diameter and 150 millimeter in height. So, all this sample, either it is a cylindrical in shape or it is a cubical in shape, and you can have a nature of the curve is like this. So, all these points you can see here, here, here and this here. So, you can have a correlation between the initial tangent modulus and the density of the expanded polystyrene geofoam material, and from this you can establish a correlation or the equation between the density of the EPS geofoam and the initial tangent modulus. That means, here is the established equation is EI is equal to 351.0 into rho minus 2633. So, what that R square is equal to 0.987. So, where EI is equal to initial tangent modulus and rho is equal to density of the embankment. Suppose if you know what will be the density of the expanded polystyrene geofoam, then you can calculate what will be the initial tangent modulus with this equation, which can satisfy this criteria. So, this equation also very useful when you will do any analysis or the finite element method analysis. So, you can, if you know that what will be the density of the expanded polystyrene geofoam material, then you, for using this equation you can calculate what will be the initial tangent modulus, and that initial tangent modulus you can directly use for your computation. So, this relationship is very much helpful to you. So, I think so far we have covered the different types of the geofoam material and different types of their density of the material, and how we are to perform that, what should be the density of the expanded polystyrene geofoam material, and also you know that how we are to calculate that water absorption capacity of the EPS geofoam material, and we find that this water absorption capacity also vary from 2 to the 4%, and which can be also considered into the design. And we have also performed that what should be the compressive strength, which is very, very important to us, and either it is a cubical in shape or it is a cylindrical in shape, and we also compile that what should be the compressive strength value at the 5%, at the compressive strength at the 10%, and also what should be the initial tangent modulus value and what should be the yield strength value of the expanded polystyrene geofoam material. And I also recommended for the Indian condition that 22 density of kg per meter cube will be the more suited, because in terms of the value of the initial tangent modulus or yield strength value. So, that will be much more this applicable as for this the observation from some other also reference on the study of the expanded polystyrene geofoam material. So, with this I finish my lecture today. Let us hear from you any question. Thanks for listening.